to the particulars, and it looks like I'm having a problem. So I'll turn off my camera. All right, so if somebody could unmic and tell me they can hear me, then I'll just continue on.
We can hear you.
Okay, thank you very much. You can mute it back.
Guys, I'll send out a link once we get them uploaded. Assuming we can get the tech to work correctly, your teachers will get the link and they'll send that out to you. Looks like Danny's back, so we'll let him take over.
All right, so can I get a Camden? Can you put your thumb up if you can hear me? All right, thank you very much. Okay, so you guys should be seeing the Kinetics screen. Is that true, Camden? All right, thank you very much. Okay, so here's the basic idea today is we want to understand why do reactions occur the way they do and understand how fast they go and how can we control that. So in order to show you that, I'm going to stop sharing this screen for a second, and I want y'all to watch a little bit of a movie script, real quick. So just, and all I want you to do is notice what's going on. So notice we have two molecules, an A and a BC colliding, but notice nothing is happening. No reaction is occurring. Now, notice when I shoot it hard enough, there is a chemical reaction. We are seeing a change. So the takeaways are it has to hit with enough energy. Notice the red line in the middle. I want y'all to keep an eye on that. So even though they hit, if they didn't have enough energy and the right orientation, it didn't work. So this one is just a bunch of molecules bouncing around. And what I want you to notice at this point is we have some product over here on the right-hand side. We made some product. And yet, if you look at this graph down here, this graph is endothermic. You end up with more energy than what you started with. But see that green line? That green line represents the average energy of the particles. So why is it that you can still have a reaction even though the average kinetic energy is not enough to get you over the activation energy, that hump? Well, if we think about it for a minute, it's the average kinetic energy. And if you watch the molecules in the box, you'll notice that they have different speeds. So notice on this far left-hand side, that gray peak over here, these are gas molecules that are only 73 Kelvin. They're very, very cold. So notice they only inhabit a range from 0 over here to 1500 meters per second. Then notice as those same molecules get warmer, they spread out. So at 173, the purple graph, notice how these molecules can get all the way up to 2200 meters per second. They still, some of them will be 0, but more of them will be going fast. And notice that as you warm up a sample of molecules, those molecules get faster and faster and faster. So where is the average kinetic energy? The average kinetic energy would be the center of this hill. It'd be the center of this purple hill. It'd be the center of this blue hill. So when we're talking about average kinetic energy, we can have a chemical reaction even though the average kinetic energy is low, because some of them are going fast enough to overcome the activation energy. And obviously, if you heat them up some more, then we will produce more and more product. But keep in mind that it's about, let me back this up a little bit. Keep in mind that this is all about collisions, right? So are we having collisions in the right orientation, and do they have enough energy? So then if you come over here and look at this next set, here's what I did. I'm going to control the amount of A and the amount of BC. So I'm going to add the same amount of both. And I'm going to click go. And this graph measures how much the reactant goes away and how much the product goes up. And what we can do is we can say in 100 seconds, this is how much product got made. Or we could say in 100 seconds, this is how much reactant went away. And that would give us some idea of rate. Now, in order to figure out things, sometimes you want to vary those. So that was 5 of A and 5 of B. Let's double the amount of A and keep the amount of BC the same. So BC, remember, is the purple molecules. And again, you could measure the rate. How fast does it get going? Now, the other thing I want you to notice is look at that graph. If you look at the graph, notice that it's kind of evened out. That graph is a sign that, hey, that's an equilibrium. The forward and reverse reaction are going at the same rate. So this time I had 5 A's and 10 BC's. And again, we can double the amount of one, keep the other one the same, and we can get some idea about how does changing the amount of chemical, how does that affect the rate of the chemical reaction? Right? So with that in your head and the idea of collisions, I'm going to stop doing this and I'm going to show you something else real quick. We'll go back to the PowerPoint, and this is probably pretty much where I'll live. Now, as we go through this, there's going to be a chance for you to work some problems, and there's going to be a chance for you to also work on, so you need like a piece of paper or maybe a calculator or something like that. That would be helpful. All right, so if we're trying to worry about how fast chemical reactions go, it all comes down to how many collisions. The more collisions you have, the faster the chemical reaction is. So we can do that a lot of different ways. If we add more molecules, we get more collisions. If we make the molecules go faster, we're going to get more collisions. Now remember, this is all in the notes that are available through A+ College Ready, and this will be recorded. So don't worry about writing this down. Go for general understanding as we go. So sometimes you want to react a gas with a solid, and that's harder to do because the solid is only going to react with the gas right there at the surface of the solid. So for example, when they burn coal, they don't throw huge chunks of coal in a furnace. They actually turn it into something that looks like baby powder, and then they blow it into a furnace. So basically those coal particles almost behave like a gas, and it reacts with the oxygen a lot faster. Obviously, if you make something more concentrated, then it makes the reactions happen faster. You've been taught before that temperature relates to average kinetic energy, and at the higher temperature, they have a higher kinetic energy. And obviously, you can use a catalyst or an enzyme, you may have learned in biology, to speed something up. And usually that has to do with orientation. The catalyst is there to help things get oriented in the right way, and thus it speeds up the chemical reaction. Just like bumper cars, if you want to hit somebody in a bumper car and cause the most amount of ugh, then what you want to do is you want to hit them either right from behind or hit them nose to nose. And behind is better because they weren't expecting it, but the faster you can get going and in the right orientation, the bigger surprise they get. So I want you to think about a piece of paper that may be close to you right now. Maybe it's on your desk or in your room. That piece of paper thermodynamically should burn. It is thermodynamically favored for that thing to burn. But in order for it to burn, you have to have enough collisions. But most importantly, those collisions have to be effective, meaning they have enough energy and in the right orientation. So will that piece of paper burn? Of course it will, but you're going to have to get it hot enough first to overcome that activation energy. There are lots and lots of chemical reactions that should happen, but they don't, only because they have a high activation energy. Sorry, that was all me. So here's a collision. We want the two greens to hit because we're trying to get chlorine to form. So we want one chlorine atom to collide with another one to make chlorine gas. So they hit each other, and then they can separate from the red and blue molecule. However, if you look at the bottom diagram, the green is hitting the red. The green is not hitting the other green. So that it will not be an effective collision. It is a good collision. It has enough energy. It just isn't effective because it's not in the right orientation. So this is very similar to the graph that we saw before. Molecules of a low temperature, it's almost like that graph gets squeezed over to the left. Molecules at a higher temperature, it's almost like you put your hand at the top of the curve and smush it down. And when you smush it down, it spreads out at the bottom. So this letter A down here, that A is important because in this graph, the A represents the amount of activation energy. So anything past this A, anything over here, represents the molecules that have enough energy to react. So if you notice, this first line, the black line, the area under the curve, that represents how many molecules have enough energy to actually start and go through the chemical reaction. When you heat the molecules up, notice how the molecules spread out their curve, and more of that curve ends up to the right of that activation energy line. So heat them up, speeds up a chemical reaction because more collisions, harder collisions, and that means more of them have enough kinetic energy to cause a chemical reaction to happen. So this is all about the FRQ. That's what we're going to train you for because that's what's coming up on the AP exam. So this is an FRQ I found from 2016 that asks you to think about collisions. So I'm going to give you 30 seconds or a minute. Go ahead and read through it. All right, so what I want you to notice is it's giving you some math, which you don't need for this particular question, but it does happen later. But it tells you you have a chemical reaction. It does bubble, so it does happen. But I want you to notice that over here, it's telling you the flask gets cooler. As the flask gets cooler, the molecules are going to go slower. So look for keywords like that. But it basically says the bubbling is rapid and slows down. Explain this change in the activation rate in terms of collisions between reactant particles. So you got two things going on. Number one, you know that during a chemical reaction, you use up reactants. So as you use up the reactants, there's fewer and fewer of them, which means there's fewer and fewer collisions. The other thing we know is that it gets cooler. It must be an endothermic reaction. So as it gets cooler, that means the molecules aren't traveling as fast, which means there are fewer collisions because the molecules are going slower. Now, I haven't looked at the answer since 5 days ago, so I don't know whether I'm right or not, but let's see. It was only worth 1 point, and basically it's saying as the concentrations decrease, collisions decrease as well. So because you've got less and less reactants, the whole thing slows down because there's fewer collisions. So you could have gotten 1 point here for saying that because you use up reactants, there are fewer collisions between reactants. And that would work. That would give you 1 point. Now, it doesn't say it, but I bet you if you said it got colder and colder molecules mean less frequent collisions, I bet you would have got the point there as well. Here's another one. Of course, there's another FRQ like that. At 30 degrees, we are thermodynamically favorable, but it doesn't happen. At 120 degrees, the reaction does occur. So remember what I said before, lots of things are thermodynamically favorable, like your paper burning, but they don't happen. So why is that? Well, it has to do with that activation energy. How much energy does it take to start the reaction? So the question is, explain how the higher temperature affects the collisions. So let's see. Well, higher temperature means they hit harder, and higher temperature means they hit more often. Because if they're going faster, faster molecules means they hit harder with more kinetic energy, and faster molecules collide more often. So as long as you're linking in your response, higher temperature means more kinetic energy means harder collisions, and they also mean more frequent collisions. They happen at a greater rate or something like that, I bet you would earn the point. The question then goes on to say, okay, so what about this? So here's a distribution for collision energies at 120. What would it look like if it was colder? Now, how do you draw this? Well, remember, this is the graph at 120. So we want to draw it at 30. So remember, when it got colder, we said it's almost like you smush it over to the left. So we want our line to start here. It always starts at 0. It goes up. It needs to go higher than the existing one. And then it needs to come down here. But it needs to end up a little bit past that line. So it needs to look something like that. Now, I want you to look at where they gave the points away. As long as you're talking about an appropriate explanation, and remember, the readers are going out of their way to give you points, but you have to connect that lower temperature means, higher temperature means greater average kinetic energy and thus more collisions. You've got to connect the temperature with the kinetic energy. That's 1 point. And then down here, you get 1 point for a peak that is above and to the left. It doesn't matter that your graph looks exactly like this, as long as your curve, the dotted curve, is smushed over to the left, is higher than the existing curve, and to the left of the existing curve, you get 1 point. And then you get 1 point for making sure your graph crosses the activation line, but is lower than the other line. So notice the question says, no reaction is observed to occur. It still occurs, but we don't know for sure. It's not observable. Somebody asked, I'm trying to watch the post y'all put, are you going to be able to draw? You know what? We don't know. They said you might be able to do it on paper and take a picture, so possibly, but when we know more information on April the 3rd, we will pass that on about exactly what that looks like. They've said phone, yes, you can take it on a phone, on a laptop, sure, or a pad like a Lenovo ThinkPad or an iPad or something like that, some kind of tablet, they think is definitely possible. So those are great questions, but we just don't know right now. So remember how I said we could measure rate of reaction by looking at how much the reactants go away or the products show up. When I was showing y'all the video earlier, that's exactly what this is showing. We can look at the delta, the change, that's what that funny triangle means, the change of reactants versus time, or the change of products versus time. That will give us a rate of reaction. So if you look at the 3 mason jars, What is the average rate of appearance of B in the first 20 seconds? Well, in the first jar, there's 0 of them. And in the second jar at 20 seconds, there's 0.46 moles of B. So how do we calculate that? Well, it's the change in B over the change in time. So it's 0.46 moles over 20 seconds. You could also look at A. You start out with 1 mole of A, you end up with 0.54 moles of A. So what's the change? Also 0.46 moles. And it happened in 20 seconds. You could also look at it between 20 seconds and 40 seconds. You could do all of these, and I challenge you to go ahead and go back and look at those and see if you can think of how that would work. But the answers are basically set out there. You're just taking the difference between measurements in time of the moles of A or the moles of B divided by how much time elapsed. Right? We could also graph this. And here's what I want you to notice. This graph is not linear. This graph has definitely got a curve to it. Well, what I want you to imagine is, I assume you've all been snacking, right? So since you've all been snacking over the last couple of weeks, I imagine that you're well versed in what I'm about to go over with you. Imagine you're sitting in a room with 100 pieces of pizza just floating in the room, bouncing around in the room. In order to eat one, it has to collide with enough energy and in the right orientation in your mouth for this to work. But you're going to eat a lot more pizza in the beginning because there's just more pieces of pizza bouncing around. So if we look at the rate of the reaction up here in the very beginning, it's really steep. There's a lot of it going away. And if we do it later on, notice how the reaction slows down. Well, of course, the reaction is going to slow down because there's less and less reactant. Katie Falk, you mentioned the notes are available on College Board. They're going to be available. These notes are available through A+ College Ready, and Matt Dean can get you those notes, or your teacher can get you those notes. Be sure you stay on and you can get his email address and talk to him. Right? So let's look at the stoichiometry of things. A lot of y'all are going to look at a question like this on the AP exam and freeze because you're going to like, oh, how do I do this? This is the stoichiometry you did in pre-AP or just regular chemistry. It's the stoichiometry you did in Unit 1. It's not hard, right? So if you look at example 2 up here, for every 1A that goes away, you form 1B. But if you look at the reaction down below, D is going to appear at twice the rate that C disappears. Well, that just makes sense from the balanced equation. If C is the number of Oreo cookies, then D could be the number of crispy chocolate wafers. Every time you take an Oreo cookie away, you produce 2 crispy chocolate wafers. I'm sorry if I'm making some of you hungry, but it's been at least an hour since I ate something at home. Right, so looking at this reaction, Q goes to 4X. Now that X is just a chemical. It's not a X like in algebra. Which component is going to have a faster rate of showing up or disappearing? How much faster? Well, the X should show up 4 times faster than the Q goes away. Or we could say who's slower? The Q is slower because for every 1 Q, we produce 4 X's. All right, so this is the kind of problem they're going to give you on an AP exam. In fact, this snapshot was taken straight from an AP exam. So ozone turns into oxygen. O3 turns into O2. Don't get caught up in this O2 delta T nonsense. All that's saying is the change in oxygen concentration versus time. So over time, it goes away at 6 times 10 to the negative 5th molarity per second. So if that's how fast the O2 appears, then how fast is the O3 disappearing? Well, you can look at this. This is a 2 to 3 ratio. So if we did the math, it would look like this. We would set it up so that things cancel. This 2 moles and 3 moles come right from my balanced equation, just like regular stoichiometry. And you can get the answer 4 times 10 to the negative 5th. All right, so what I want you to do is you take a minute and look at it and see if you can work out the math. So we'll give you like a 1-minute clock and see if you can find A and B real quick. That's pretty darn close to a minute. For those of you who feel like you don't really know what's going on, keep track of where you are, write this kind of thing down, go back and ask your teacher, hey, where did they get this answer? I didn't quite understand this kind of a thing. Because the goal is to make y'all feel comfortable with the content to prep you out for the AP exam. Y'all are going to do fine. It's just a matter of we want to be able to answer your questions. So if you have questions along the way, make sure you write them down and you can ask your teacher. If we look at the answers, the answer for NO2 was 8.4. The answer for O2 was 2.1. And that's because of the ratio of N2O5 to O2. So for every 2 of those, you only get 1 O2, so it's half the rate. For every 2 N2O5s, you get 4 NO2s. So that's going to be twice the rate. You could state, no, you can state the rate of decomposition as whatever, but here's what I don't want you to get caught up in the negative and positive signs, because if they do that on the AP exam, then they have to grade you for making casual mistakes. So let me ask you this. If I said, what is your change in weight? And you said 10 pounds, I would think that meant gain 5 pounds. But when they say, what is the rate of appearance? They're assuming that that answer is positive, it's growing. And when they say the rate of disappearance or decomposition, that implies that it's going away. So you don't really have to use a negative or positive. The appearance decomposition takes care of that. If they did that to you on the AP exam, they'd be grading something extra that they didn't want to grade. Right, so there's 2 kinds of rate laws in the world. We're going to do differential rate laws today. If we can get that done, then I'll be happy. In the next one, we're going to talk about something called the integrated rate laws. So, most important thing, when they ask you to write a rate law, you write rate is equal to little tiny k. If you've done equilibrium, you've done big K. This is not big K, this is little k. So we write rate is equal to K times the reactants raised to some power. Now, if you've done equilibrium, I just need you to clean that out of your head. Equilibrium and kinetics are 2 different beasts. So in equilibrium, we put products over reactants. We use coefficients as the exponents. That is not how we do kinetics. For kinetics, your exponents are going to be 0, 1, or 2. That's pretty much what they're going to be. We don't get them necessarily right from the balanced equation. We find those exponents by looking at experimental data, right? So if this m over here is a 1, then we would say it's first order. It has an order of 1. If it was a 2, we would call it second order. So rate is equal to k, write all the reactants, and then you'll have to figure out the power. So let's see how we do. We compare the rate laws to figure out those exponents. So let me go over and then I'll come back. So this is in your notes, so don't worry about it. But let's look at a set of data and then we'll come back to this in a second. All right. Now, in order to look at the ammonium, the NH4 concentration, and what effect it has on rate, I need to find 2 places, 2 trials, 2 experiment numbers where the NH4 changes, but the NO2 doesn't, because we only want to do 1 at a time. So we can go back and look. We're going to do the rate of one experiment compared to the other. We're going to do the whole rate law over the whole rate law. We're going to fill in all the numbers we know from the table, and then we're going to solve for what we don't know. Right? So look at this and see if you can find 2 experiments where NH4 changes and NO2 doesn't. Or maybe you can find 2 NO2s where it changes, but the NH4 doesn't. All right? And you can pick any trial that changes, but the other ones kept constant. Doesn't matter what trial you pick, but these are the ones I picked. There's our reaction. I'm going to compare experiments 1 and 2. So NO2 stays the same, but the NH4 basically doubles. So let's write out the rate law for each one. So this is trial 2, experiment number 2. I write the rate from the data table. K, we don't put in a number for K. The 0.02 raised to some exponent m. The 0.2 raised to some exponent n. That so far is so good. Don't worry about the stuff to the right. That's not supposed to be in there yet. I filled in the other stuff. Now, let's see what cancels. The K's cancel because you got K on top, K on the bottom. The 0.2s cancel because they're the same. In other words, nothing happened. So basically what we get is the concentration of the NH4 doubles. It goes from 0.01 to 0.2, and the rate also doubles. So 10.8 divided by 5.4 is 2. 0.02 divided by 0.01 is 2. So 2 to what power is equal to 2. So our exponent for that is 1. All right, so let's do the other one. So we need to pick out 2 that we can do this with. I'm going to pick these 2 just because what's life without being hard. In this particular one, we didn't pick 2 where NO2 changed and NH4 was the same. But I would challenge you to go back and try one where the NH4 was the same and the NO2 changed. And the reason why I did this was I'm going to show you that even if they're not the same, you can still make it work. So let's look. Notice this time we copied down the rate. We have the K, but this time we filled in the exponent 1. We figured out before that this was an exponent 1. We said it was first order. Here's the data from the second one, from the 5th experiment. And if you lay out those rate laws, you can look at it and go, okay, what's the same? What can I get rid of? And we can get rid of, we can get rid of these Ks, My bad. One more time. So we can get rid of these Ks. This is 0.06 over 0.2. So we can do the math and get that the change in rate is basically 3. The change in concentration is basically 0.3. And the change in concentration here is 10. And once you do all that math, you get that N is equal to 1. So in other words, it's first order with respect to NO2, first order with respect to NH4. Katie, if it was a Star Wars joke, I didn't intend for it to be, but if you thought it was funny, laugh. All right, so what that means is we've written the rate law. I didn't put the ones in because it's understood to be 1. K is the rate constant. So how do we find the rate constant? We pick something from the table and we plug it into the rate law and we solve for K. So let's see what that looks like. Any trial at all. I happen to pick trial 7, but you can pick any trial that you want to. You can always go back and try it again on your own. But what you'll notice is that if you plug in any trial, you're going to get a value of somewhere around 2.7 times 10 to the negative 4th, or 0.00027. Now, you also have to worry about the units of K. And what I encourage my students to do is don't try to do it all at once. Do one math problem where you work out the math. Do the other math problem where you work out the units. So this rate was in meters per second. These two were molarity. So if you ignore the number, you get molarity per second over molarity squared, and you come up with these units. So can you write a rate law? Can you find the value of K? Now, this is the part where you get to go tonight, and when you're sitting at dinner or doing whatever with friends or parents or brothers and sisters or whoever it is, I want you to tell them how much you learned today. You could say, oh, the rate law is equal to K, of course, the rate constant times this reactant times that reactant, which has an overall order of, the overall order is just add up the exponents. You sound bougie and smart, but you're not really. All you know is that you added up the exponents. So if we had had 3 reactants, you'd add up all 3 exponents and you get the total overall order. All right, so here's what you ought to be able to do. Can you look at a data table, and from that, you can figure out a rate law? Can you calculate a rate constant once you have a rate law? And can you determine the overall order by adding up the exponents? All right. Now, as far as calculator or no, I got to imagine they're going to let you use a calculator on the free response portion on this year's exam, but we won't know till April 3rd. So right now, just go ahead and assume that, yes, you get to use one. Right. So y'all take a stab. See if you can write a rate law. If you want to use a calculator, that's fine. Go ahead and take 1 or 2 minutes and see if you can write a rate law for this one. So if you're stuck, remember that rate laws start with rate is equal to K. times the concentration of each reactant raised to some power. All right, that's been somewhere around 2 minutes. So let's see what we did. So the rate law should be rate is equal to K times NO squared times H2 to the first power. Now let's see if we can figure out why. When the NO is doubled, the rate basically goes up by a factor of 2 as well. When the amount of H2 doubles, this one goes up by a factor of 2. So let's look at the answers real quick. So if you were able to write the rate law, you could look at it and go, okay, I see what's going on. If you needed to find the overall order, that would be simple. If the NO2 is squared, it's second order, and the H2 is first order, then that would be an overall order of 3. Now, how would you find K? Well, to find K, you take your rate law, whatever it is, and you plug in one trial. Now, a tip for the AP exam, what if you got the rate law wrong? What if you got that they're both first order? Well, you wouldn't get that point, and that's okay. But what if you plugged in one of the trials into your rate law and you solved for K? You would still get that point. As long as you were using the answer you had before to solve that next problem, they would have to give you the point. They're very forgiving that way. So even if you make a mistake, it's okay. Right? So the rate constant, pretty easy. We just plug in and solve. Now, what about part D if I'd given you part D? When NO is 0.01 and H2 is 0.01, how could you solve that? Well, if you look at the rate law, the rate is what you want to know. The K, well, you already solved for that. The NO is 0.01. The H2 is 0.01. So if you have 0.01, 0.01, and the value for K, you can actually find the rate when you plug in that new set of concentrations. All right, so for this last one over here, well, not last one, just take a look at this sample problem. See if you can find the rate law. There's your equation up top. See if you can find the rate for trial 5, and don't worry about part C. For right now, just see if you can find the rate law and what is the rate for trial 5. I'll give you a couple minutes to take a stab at it. William, I'll go back over how to find the units for K. For right now, just go ahead and see if you can get the rate law. So you've had a chance to take a stab at it. Let's see what those answers are. And remember, the trick here comes into practice and stuff like that. And the trick comes into knowing what you're going to ask your teachers. Like, this is where I got hung up. Somebody asked about how do you find the units? That's great. Those are great questions. Just remember that it's really hard for me to teach 200 of y'all all in one thing and answer everybody's question. So keep track of what your questions are. So let's look and see what the rate law is. Well, what does every rate law start with? Rate is equal to K times S208 raised to some power times I minus raised to some power. So let's see what those powers are. So how did we know that to be true? Well, when this one goes up by a factor of 1.5, so when we go from S208 from 0.018 to 0.027, we do this bigger number over the smaller number. So the rates is equal to the K compared to the concentrations. When this one goes up by a factor of 1.5, this also goes up by a factor of 1.5. So 1.5 to what power is equal to 1.5. That's where we get the exponent of 1. To find the I minus, we want to find a place where we can look at and try to solve it. But notice there is no place where I minus is changing, that S208 stays the same. But we already know the exponent is a 1. So we can do this. The 0.036 compared to the 0.018, we know the power of that is 1. 0.054 compared to 0.036. So we can do the math and say the S208 is going to double, which means the rate will double. So that 2.6 should make this sucker go faster by a rate of 2. And then when we go from 0.036 to 0.054, that's basically like saying it speeds up at 1.5 times that speed, right? Because that goes up by 1.5, and this one already doubled. And then what other change occurs? So if you set up the rates compared to the concentrations, just like we did before, you would see that they both have an exponent of 1. Now, how can you find the value for K? The K is just any trial and plug it in. And then how would you find this? Well, the easiest thing to do is just find the value of K, plug in right here the concentration, and the value for K, and what you will spit out is a rate. So in other words, you're looking for the rate, you found the value of K, the S208 you know is 0.015, and the I minus is 0.040. Plug that in and solve, and you should get this answer, 2.4 times 10 to the negative 6th. Now, keep in mind, that's the rate of disappearance of S208. How fast should the I minus go away? Well, that is nothing that we can solve from this table. That goes back to this original equation. For every 1 S208, we're going to get rid of 3 I minuses. So if the S208 goes away at 2.4 times 10 to the negative 6th, then the I minus should disappear 3 times faster. And 3 times faster is 7.2 times 10 to the negative 6th. Right? Now, one thing I want to touch on, and then I'll go back to that question about units, and then we're done. So what I want you to notice here is the you can have a pseudo rate law. So a pseudo rate law is, I don't want to worry about both of these like we did before. What if I want to only worry about one reactant? Well, the way you worry only about one reactant is we change what we're doing. So instead of these values, which were given to us in the table, let's make so much I minus, let's make it 100 times more concentrated than it was before. The I minus is not going to change. There's so much of it that it doesn't matter how much S2O8 gets used up, the I minus just won't change appreciably. Go back to the pizza idea floating around the room. Before I gave you 100 pieces in the room. What if I gave you 100 billion pieces of pizza in the room? Trust me, you can be super hungry and bored, and you're never going to make a dent in 100 billion pieces of pizza. There's just so much, it just doesn't matter. So we can take these rate laws that we write and we can move them around just a little bit, where we can take the rate law that we wrote here and we can change it to this new, what we call a pseudo rate law. A pseudo rate law is similar to the original rate law we wrote, but it only worries about one chemical at a time, right? So just realize that sometimes you'll see a pseudo rate law, and all they're asking you to do is explain why that works. Well, a pseudo rate law is based on the idea of I can change my rate law by making the other thing so concentrated that it just doesn't matter. Right? So somebody asked a quick question about, hang on. Sorry, somebody asked questions about units for that last one that we did. How do you find the units of that? And let me show you, I worked on this real quick while you guys work on that other problem. Hopefully it comes up. All right, so in that previous problem where you had to find the units of K and stuff like that, the rate law was, the first one was molarity squared, and the second one was molarity to the first power. I'm not putting in numbers, I'm just putting in units. So the rate was molarity per second, molarity squared, molarity first. So all we have to do is rearrange. So I get K on one side. So K is going to be equal to molarity per second. And also on the bottom are going to be that M molarity squared and molarity first. All I did was like rearrange algebraically. And so I found that K is equal to 1 over molarity squared seconds. And that's because you got molarity on the top, molarity cubed on the bottom, and you can cancel out the molarities to give you 1 over molarity squared seconds. Hopefully that helps. Right, so that's the last thing I got for this one right here. Thank y'all so much for dealing with me in trying to teach y'all, and for dealing with all the stuff that we're doing. And hey, if you have questions, please let us know. Let us know how we can help you. With the new exam, y'all can totally do this. With the new exam, the fact that they're not going to ask you about acids and bases, y'all can totally rock it. All right, we'll see y'all next time.
All right, guys. Some of you emailed me about copies of the notes and the FRQs that Danny used. I'll be sending those here momentarily. Our next one of these is on the 30th, March the 30th at 2 o'clock. It'll be a continuation of kinetics. We max out at 250 participants in these Google Hangouts. Today we maxed out, so get in early. I am going to record them. I'm going to try to upload the first recording today, and I'll send a link to your teachers. But thank you guys for coming, and I hope it helped. See you soon. Thanks, Danny.
You're welcome, you're welcome, you're welcome, you're welcome. Peace.